Good evening, everyone, and welcome to the 2025 Drake Awards. I'm Marco Larsen, and I have the honor of serving on the board of directors at the SETI Institute and being your host tonight as we celebrate science, curiosity, and the people pushing boundaries of discovery. I'm also glad to welcome David Decker, who will be helping with tech and saving us, I hope, from any hot mic moments. Whether you're tuning in from across the country or across the globe, we're so glad that you're here. While our in-person audience gathers in California, this space is just for you. An exclusive program with special guests, live segments, and a few surprises. Tonight, we celebrate something far bigger than ourselves: curiosity, discovery, and the relentless pursuit of understanding. The SETI Institute exists for a purpose as bold as it's beautiful: to explore, to question, and to advance our understanding of life in the universe. I joined the board for one reason, because I believe the work happening here at the intersection of science, imagination, and courage deserves to be seen and celebrated by a much larger audience. Because in a world overflowing with noise, this is the stuff that cuts through. The SETI Institute exists to pursue one of the most profound and thrilling questions of our time. Are we alone? That mission isn't just scientific, it's fundamentally human. It speaks to our shared longing to understand our origins, our place in the cosmos, and what possibilities might lie ahead. The science here isn't just extraordinary, it's essential. The scientists who ask impossible questions, the educators who ignite the next generation, the partners who build and believe, and the supporters, like many of you, who make this all possible. Tonight, we honor those who lead the way. Our honorees represent the very best of what science can be: brave, uncompromising, expansive, hopeful. Their work pushes the edges of what we know and dares to imagine what might be out there. So here's what I ask of you tonight. Lean in, listen closely, and let yourself be moved, because the stories you're going to hear aren't just about science, they're about us and what unites us, what drives us, and where we might be headed. Thank you all for joining us from wherever you are. And please let me first thank my fellow board members and important sponsors. For the Drake Award, Avery Wang and Katja Relt-Wang, John and Carol Giandrea. CSC Directors Award, Elizabeth Farghese and Matthew Veeden. SETI Forward Award, Christine Dawood. Reception sponsor, Amaresh Kolipara. Virtual sponsors, Dane Glasgow, the great Jill Tarter, and NFP and Aon Company. And supporting sponsor, Breakthrough Listen. For our online audience, we have some very special guests joining us tonight. 3 previous Drake Award winners and one of our newest stars: John Rummel, Paul Horowitz, Bill Borucki, and Sophie Clark. Now, I also like to thank, with all due respect to Bill Diamond and the other luminaries enjoying dinner in the main hall, that this is kind of the VIP room. We get to hang out together. We've got all the perks, of course, the bonus footage, exclusive interviews, and yes, that mute button right there, which, let's be honest, is a luxury not available to everybody at dinner, at least not gracefully. Nick is my dear friend and co-producer on a new docuseries we're building for the SETI Institute. Nick's an artist and producer. He works out of Brooklyn. His work centers on a big, timeless question, which is how and why we communicate, which is certainly important to me. To chase that down, he's done just about everything from paintings, sculptures, podcasts, theater, television, really all of it. All of it rooted in, I think, human connection, the signals that we send each other. Nick also serves on the board of the legendary public arts organization, Creative Time, which you may have heard of. And he's one of those rare collaborators who makes the work deeper, smarter, and just more fun, Nick. A few years ago, I produced the Morgan Freeman PSA, which inspired us to go bigger. Many of you have already seen that. But we wanted to create a new series built around awe and relevance, something that's designed to broaden our mission to reach the billions of humans we haven't had the chance to inspire. And David, if you don't mind, why don't we just start off with playing that clip first to get us started here? Well, guys, it's fantastic. And eventually we're going to get to that in just a moment. But why don't we start with our conversations, and then David, we can get back to that if that makes sense. So let's first meet our extraordinary honorees, Dr. John Rummel. Dr. Rummel is the 2023 recipient of the Drake Award, and he spent his career championing astrobiology and planetary protection. At NASA, John served as senior scientist for astrobiology and as planetary protection officer, two roles that have helped shape how we search for life while safeguarding our cosmic neighbors. It's an interesting thing that we're going to be discussing. His work has set foundational policies in DC and beyond that continue to guide astrobiology research around the world. And funny enough, I noticed that John has Sugar Daddy at the end of his title, which I found kind of curious, which I'm sure we're going to be getting into. Paul, maybe you can allude to that. Next, Dr. Paul Horowitz, our 2021 Drake Award winner, is an emeritus professor of physics and electrical engineering at Harvard. He's a true pioneer of SETI instrumentation, designing the first million and billion channel receivers and leading the construction of the first dedicated optical SETI telescope. His innovations have expanded our ability to listen and to look for signals of intelligence in the universe. Paul's inspiration from Carl Sagan and Frank Drake spans 40 years. And we also have Bill Borucki. Bill is a trailblazing NASA and SETI Institute scientist whose work has shaped modern space exploration. Before leading the charge on NASA's Kepler mission, which revealed thousands of exoplanets and transformed our view of the galaxy, Bill was already making history. In the early days of his career, he developed heat shield technology that helped bring Apollo astronauts home safely. He later became a champion of transit photometry, a once controversial method of planet detection that is now a cornerstone of exoplanet science. And finally, Sophie Clark, one of our newest stars, this year's REU Award of Excellence recipient. Sophie is an undergraduate at the University of Florida whose work during her SETI internship blew us all away. She explored protoplanetary disk winds, which is a complex area of astrophysics, and built a model to interpret James Webb observations of young stars. Sophie recently graduated with a BS in physics and astrophysics and will begin her PhD in planetary sciences at the University of Arizona. So I think that this is a good time for maybe Paul. Can you give us a little perspective of what you've been doing? And I think that's going to set the tone for our conversation with John, Bill, and Sophie. Give us a little perspective on what you showed us before in terms of where we are, what you've been studying, considering your incredible history.
I'm sure, happy to do so. But I should mention why John Rummel is Sugar Daddy, which is John.
Yeah, please.
I don't
Thank
remember,
you.
but
And I'm sorry about that, John, but it's just, it is on your resume.
Back in the 80s, we were at NASA and we were building Beta, and I came hat in hand, and you were wonderful. You sponsored Beta for a year and a half or 2 years, and maybe you don't remember this, but we had never gotten government money before or anything from NASA for SETI. And I didn't know that when you write progress reports, you're just supposed to write a page or two of what you've been doing. So I wrote these long tomes, each of which could be a chapter in a book on signal processing and radio astronomy. I don't know if did you read those things, John?
Yeah, many more like it.
Yeah. Anyway, okay, so to respond to the thing, let me just share a screen here. Let me click this thing along here. So this is something I like to show. It's not fresh this year, but it's always fresh because it tells you something about where we sit in time. We can do an analogous one for where we sit in space. So can you guys see this little screen here, our place in time?
Yep.
So, it's easy to think things have always been the way they are or kind of the way they are. And that gets it completely wrong. We are in a unique little situation. Let me just let me flip through the Earth's history in 1 minute here. So if we map the time from the Big Bang to now, that's about the new number is 13.7 billion years old. The sun and the planetary system about 4.5 billion years old. And if we call that thing one day, we sort of get a sense of how long things take. So here it is. Earth is formed, hot, big bombardment, but not very long after that, life arises. This is surprising. You know, it didn't have to start like that. Suggests that this may be a pretty common occurrence. But, you know, it was kind of boring life. It was like pond scum. It took until just a few hours before midnight in this one day of the Earth before we had multicellular organisms. So let's expand the last hour. And here we are. And now we have some interesting multicellular things like dinosaurs, which go extinct, as you know, 65 million years ago, whatever the great asteroid, the Louis Alvarez asteroid. So what happens? Let's go here to the last minute. And by the way, the time scale here is 50,000 years per second. The last minute, now we have animals roving the Earth, but Neanderthals, the kind of things that we'd recognize just in the last few seconds. Let's expand the last second. Now we're getting interesting. Here, 0.2 of a second, that's up 10,000 years ago. The beginnings of agriculture. 5,000 years ago, recorded history. That's 1/10 of a second before midnight. Let's expand that. Here's the last 1/10 of a second. And now things get really interesting. Now we have Jesus and Columbus and Marconi and lasers and radio telescopes in the last millisecond. Why the hang up on lasers and radio telescopes? Because if we want to communicate with other civilizations, we're going to have to use technology that spans the cosmos, something like that. Well, we live in this little sliver here, itsy weensy little sliver, and look at the kind of amazing things that have been happening, and you know what's going to come. Amazing stuff. So it hasn't always been like this. This is now, and this is amazing. Let me just flip through another thing. This is a picture I showed. Dan Wertheimer and I shared the Drake Award back a few years ago, and I just wanted to make a little graphic then on the scale of this last 2 milliseconds. And we started with Frank's birthday, since this was a Drake thing. And Frank was born just before the origins of radio astronomy, which is Jansky in 1931. Here I was born. Here Dan was born. Here spectral lines were first discovered by Ewan and Purcell at Harvard. And here's Frank's project, Ozma, 1 channel. And here we are a millisecond before now. And suddenly we're building these analyzers, radio analyzers, 100 channels, 100,000 channels, 8 million channels, 270 million channels, 5 billion channels, and now we have 30 billion channels. The rate at which we're expanding into this last millisecond of history is remarkable. It really means that we have a chance of finding these signals. Let me just flip through a couple last things. Just to say, what are we doing now? We're working with optical astronomy now, not those multi-channel analyzers. And this project is based at UCSD. That's Shelley Wright. And the kind of telescopes we're using now are Fresnel lenses. Rather than mirrors, we use these plastic things. And we've been building telescopes that look like this. Here's a picture of one of these telescope modules. Here's some electronics. Here's some more goodies. We love goodies. And we've now putting these things on Palomar. Frank Drake, by the way, was quite interested and a member of our team until he died a few years ago. What we're doing now is we're in synergy with the gamma ray astronomy people, because both extraterrestrials that we're looking for might make flashes of light in the sky, and so do high energy incoming particles. Their noise is our signal and our noise is their signal, but it turns out these telescopes are great for both. So we're putting up right now 6 of these things on Palomar to look for both possible flashes from extraterrestrials and, my last slide, these kinds of things, which are naturally occurring cosmic ray induced Cherenkov radiation. And because the radiation only lands in a fairly small space, rather than having one giant telescope, what you want to do is build a whole bunch of little telescopes. And so that's what we're doing. And it's a really exciting project. I'm going to stop.
And actually, Paul, it's fascinating. We're gonna get into a little bit of this with Anne Marie Cody later, as you mentioned. I'm wondering if you can give our audience some perspective of how your work led to what Jill has been doing, and Andrew Simeon right now, and of course Allen Telescope Array. If you can maybe make those connections for us.
Well, sure. Well, we know Jill because we saw the movie, right? So
Yeah.
sure. Well, SETI started way back. Marconi listened for signals, and there've been proposals to look for, things on Mars and all that kind of stuff. Basically, the heyday of the beginnings of Sirius SETI were back in 1960 with Frank Drake and radio astronomy. And the Allen Telescope Array is a radio array. And Jill Tarter, we saw the movie. She was using the VLA, at least in the movie. And
Right.
that's been the dominant mechanism. But Charlie Towns, the man who won the Nobel Prize for the invention of the maser and laser, pointed out that optical signals go through space perfectly well. That's why we have optical astronomy. And in fact, when you look at the technology of it, they're fully as plausible and as reasonable a mechanism for communicating between stellar intelligent civilizations. Oh, I just saw a dog go by there.
Yeah, that's my junior. Hey, buddy.
As radio. So right now, at least our team in California, it's Dan Wertheimer at Berkeley, Shelley Wright at UCSD, my former student Andrew Howard at Caltech, and myself at Harvard, and a team of other people are building these telescopes. And the connection now is we're doing optical, and Breakthrough Listen is doing mostly radio, and that's the thing that Jill has done, and Andrew Simeon with the Hat Creek array and so on are in the radio business.
Thank you. No, that is fascinating. So, John, you were way ahead of your time in terms of signing checks and, getting this work promoted when it wasn't very popular. So what was it that you saw? What was it that inspired you either about our Drake Award winners, the SETI Institute, the science itself? Like, what was it that put you into our corner?
Well, it wasn't too long that the SETI Institute was awake and alive that my predecessor at NASA headquarters started giving them money. That was the whole point. Don DeVincenzi, who recently passed away, had been given the portfolio for exobiology, but he wanted to move back to California to be with his family. So he was on the lookout for some poor sucker that would come and take over the portfolio. It turned out that one year in 1986, Don initially said, "Can you come and help me out a little bit? Just maybe 25% of your time." And I recognized this thread from Bilbo Baggins getting stuck with something, because the next time I saw Don, he goes, "Just 50%, John, just 50%, no problem." End of that week, which was the ISIL meeting in Berkeley, Don was up to 75%. And I was on a reserve week with the Navy when Don calls up and said, "Can you come down and talk to me over the weekend?" So we don't have weekends. But anyway, so I ended up going down there, spending the night at Don's house. He gave me, kudos for having written down all the different tasks that were going on. And when I got back to California, I was told basically, be here on October 12th. So October 12th, 1986 is when I had given up and decided to go as much of the world as Don wanted. And 2 months later, he left me with this portfolio saying basically, you'll just do the job until we find somebody to replace you. And the next thing you know, they found somebody to replace me, and it was me.
Wow. So I guess we owe a little bit to you then.
I always refer to that in planetary protection as great pirate Roberts jobs, because nobody tells you that you're going to be taking that job, but they just kind of all disappear.
Well, listen, that's funny. I'm glad you bring that up. So planetary protection and planetary defense are two different things. Right. I'm wondering if you can give us a little explanation of the difference, so people understand the work that we're doing versus, say, NASA, where this is concerned.
One of the first things I did at NASA headquarters is give everybody on the advisory committee a picture of a large impact event on Earth and it basically says the dark side of exobiology, because we have to live with a solar system that involves things running into us and doing a little bit of damage. At the same time, I pointed out how important it was that the microbes that we had enslaved years ago were available and could be domesticated. So you take something like this, Sierra Nevada.
Hey, there you go.
That's basically a domesticated microbe. And we're not sure who's domesticated whom in this particular case, because when we're brewing up a beer, we're doing it with a lot more enthusiasm than the yeast can do it on their own. Anyway, it turned out to be a very interesting portfolio, and I was interested in being interested. So that I was basically told that if I didn't take the job, it would go away, because the new people coming in didn't like exobiology, thought it was a bad idea, had dealt with Senator Proxmire, and therefore, if I opened up the gate and walked out the door, things would disappear. Lynn Harper was working real hard at the time to make good things happen in the case of things like technology, instruments, etc. And we had other people who were working on planetary protection, which is basically keeping Earth microbes from destroying other habitats and erasing our ability to tell what's going on, or also to prevent people from bringing back things that might kill us all.
Right.
Now, the large impact events, planetary defense. Small Sierra Nevada pale ale, that's planetary protection.
Well, listen, and John, we might have to recruit you again in today's current atmosphere to help us on Capitol Hill, if you don't mind. Bill, I'd like to go to Bill before Sophie quickly. Bill, I'd love for you to chat with us about Kepler. Everything that Kepler is doing. Of course, we're going to cover that a little bit with Anne-Marie later, but would love to hear more about that, which sets the stage for what Sophie's been doing with Webb.
Well, of course, one of the things that Kepler was able to accomplish was come up with one of the factors in the Drake equation. And I think that was one of its proudest achievements, because that's a very important equation in terms of our understanding of intelligent communicating life in the universe. But it by itself, though, we have learned a lot about other planets and planetary systems. Most of them are very, very different from our own planetary system. And certainly the planets have a wide range of types that we've never seen in our own solar system. Some of them almost as heavy as iron, others are built like styrofoam. They're as big as Jupiter, they're like styrofoam. For example. You got planets that are basically molten lava planets. Lots of planets in a habitable zone, but no planetary system anything like our own solar system. One of the interesting things, of course, that was obvious early on was there were people finding Jupiter-sized planets, and Jupiter's an enormous planet, in short period orbits, 1 day, 2 days, a week. And so that was a scary thing, because that was discovered before Kepler flew. If you have planets like Jupiter with a 4-day orbit, a week to orbit, almost certainly they formed out where Jupiter formed, where there's a lot of material to form a big planet. So they must have come spiraling in, and that would not have been good for any small planet in their way. They would have cleaned them out. And they may have populated the galaxy with stray planets, and we see a lot of stray planets. So it was a real concern. Would Kepler find any small planets, any planets in orbital periods like that of the Earth? And it turns out, yes, indeed, the formation of Jupiters isn't anywhere near as frequent as the formation of small planets like Earth and even smaller planets. Another interesting discovery that's particularly important here is that we found that most stars have planets. There are more planets than stars. Many of these planets are in a habitable zone where life might exist. And consequently, that means there's an awful lot of targets, an awful lot of possibilities for life in our galaxy. If we had found the opposite, most stars didn't have planets. The Jupiter swept them up, for example, and got rid of the little guys. That would have been the opposite story. In that case, funding and optimism to go ahead with these searches, which have to be so dedicated, and yet, up to now, they haven't found lots of people saying hello. We're all looking forward to that. But at least we know now there are planets out there. They're in a habitable zone. We should keep looking. So that's a little bit of what.
So, Sophie, you're sitting with absolute legends. Does this still, I mean, obviously, I mean, how does it inspire you? And we want to hear a little bit before we go to break about your experience at the Institute this summer, the convergence of all these disciplines under the Drake equation. How was that for you? Obviously, you performed exceedingly well and are doing some really important stuff. So again, how does it feel being with these guys? And how does this realization inspire you in your work?
Yeah, I mean, if I could talk to myself 4 years ago when I was first starting my undergrad career, I would not have thought that I'd be on a Zoom with these people right now. So it's very cool to, be among legends, as you said, talking to people about SETI. Yeah, my experience at the SETI Institute kind of opened up my whole idea of what science could even be in a way. So I originally was very focused on being just in the astrophysics area. I'd done internships on astrophysics in the past, and it was only when I came to the SETI Institute that I was among people doing different kinds of research. I had people at the desks next to me doing actual chemistry research in the lab, some other people actually looking for technosignatures, some people mapping Mars. So it was very cool to see how all of us were working on such different things, but they all kind of fell under the umbrella of SETI. For me, it was very cool to be able to connect what I was studying and the actual observations that are being made with Webb today to the eventual development of planets and life. It was just a very full circle moment for me, and it made astronomy feel like a lot more, connected to all of us in a way. So it was very, very cool.
Here, here. Here, here. Guys, we are at time right now for the moment. We're going to go back to the event, but I want to give you a warm online applause. We thank you all for joining us. It's really amazing to be with all of you guys. We'll see you in a few minutes.
Finding life beyond Earth is no longer a dream. It's a discovery that will likely be made during our lifetime, and it will change everything. We've been here for more than 36 years, at the forefront of a quest that many consider science fiction.
Mars is the closest planet where we might find the possibilities of alien life.
We are home to over 100 explorer scientists.
It just takes your breath away.
Our purpose is singular.
It's kind of best to understand what you have in your own backyard as you're looking up into the cosmos.
To understand the origins and prevalence of life in the universe.
What we are doing is to try to understand, are we alone in the solar system?
Why do we pursue our mission? Because the discovery of life beyond Earth will lay the framework for humanity's next steps to the stars.
We are trying to understand why we even exist.
We are the SETI Institute.
Hello, everyone, and welcome to the Drake Awards. I wanted to thank you for being a part of this very special evening, whether you're here with us at the Computer History Museum or joining us online. I'm Nadia Drake, and I will be guiding you through portions of this evening's program. I am a science journalist, a former scientist, a member of the SETI Institute's board of directors, and my favorite title is that I am Frank Drake's oldest daughter. And my sister is here too. More than 60 years ago, as Dad dreamed of alien worlds, he tackled a question that at that point only existed at the fringe of science. Are we alone? And he didn't have a crystal ball, but if he did, he would have looked into it and seen a future in which his creativity and his courage and his intellectual humility helped form the foundation for an entire field of science that we now call astrobiology. Now, Dad was many things, and perhaps chief among them, he was a force for good. Tonight, we come together in that spirit to celebrate curiosity, discovery, and achievement, and the willingness to not only ask really big questions, but to take on the challenge of answering them. Our mission at the SETI Institute is to lead the quest to understand the origin and prevalence of life and intelligence in the cosmos. How did we get here? And how alone are we? These are really big civilization scale questions, and leading the quest is a lofty goal. We will not succeed if we do it alone. And so we rely on a very strong community of supporters, of scientists, educators, innovators, of partners, people like you and me, who are inspired by grand quests and who, like Dad, dream of alien worlds and find an intellectual home in the universe of hard problems. Tonight, we're going to introduce you to some of the stars of our community, this year's honorees, who have made exceptional contributions to science and exploration, some of them over decades, some of them at the very start of their careers. And I am so excited for you to meet them and to get to learn more about their work. I hope that you enjoy the program that we've put together and that you enjoy the stories and the people and the ideas that we're celebrating tonight. And now it's my pleasure to welcome our fearless leader, Bill Diamond, the president and CEO of the SETI Institute, to the stage.
All right. Thank you so much, Nadia. And when Nadia mentions that her father was a force for good, the most and clearest evidence we have for this fact is that one of his favorite things to do was to serve ice cream. And anybody who loves to serve ice cream has to have a big heart. So that was Frank. And those of you who know and went to the ice cream socials at the SETI Institute and were served ice cream by Frank Drake know exactly what I mean. And we still do that in his honor. So tonight, I'll just start with a little side note, which is there is a somewhat well-known person in a relatively well-known address somewhere in the District of Columbia who is rather notorious for going off script. No names. I will tell you also that my team live in abject fear that I will do the same thing, because they know once I get started, it will be 2 hours before I put the mic down. So I told them, look, don't worry. I will bring a script. That will keep me honest. It will keep me on time, because Nadia said, if you go over time, I'm going to yank you right off the stage. But also, applause. One of the benefits of having a script is, of course, having some detailed information that I would otherwise not be well equipped to remember. So without further ado, let me issue my welcoming remarks. So first of all, we're delighted to have you all with us tonight, both in person and online, to celebrate science and both the relevance and the importance of human endeavors to investigate some of the most profound questions of our very existence. How does the universe work here? And how did life form on this ordinary planet around an ordinary star in one galaxy among billions? And are we alone? Our quest involves partnering and collaborating with federal agencies, academic institutions, private industry, and private philanthropy that together fuel our mission to lead humanity's quest to understand the nature and prevalence of life and intelligence in the universe. Tonight, we gather to acknowledge the progress made in just the last year in the many fields of science our research embraces. We're here to honor the scientists at the SETI Institute and their colleagues worldwide who work diligently to address our fundamental questions, and in so doing, help discover why we even exist and what it means to be human. In this context, it is particularly relevant to be honoring two gentlemen in Dr. John Baross and Dr. David Deamer, both of whom have been working on the very basic and yet highly complex question of how life began. There are many people to thank for making tonight possible, including our generous sponsors, our donors, our partners, and our staff. We'll introduce our specific award donors with the award presentations. But before we get further underway, I want to thank Trustee Amaresh Kalapara for sponsoring the reception. It was quite good. Trustee Dane Glasgow and founder and trustee Dr. Jill Tarter, and our 403B partner, NFB, for sponsoring the virtual event, with the irrepressible trustee, and the board members here know who I'm talking about, Marco Larsen serving as host. Our partners and collaborators at the Breakthrough Foundation are also sponsoring and supporting tonight's proceedings. So thank you all very much. But none of us would be here this evening if it were not for the efforts of a pioneering young woman astronomer who decided to become an astronomer at a time when women were not even allowed in observatories. I'm speaking, of course, of Dr. Jill Tarter, AKA Ari Ellaway, who is here with us tonight, almost halfway through her 82nd orbit around the sun. And I would love to have all of us give her a warm welcome. And we're all very blessed to have Jill with us tonight. Additionally, we wouldn't be here this evening without a 41-year collaboration with NASA. And it's worth noting that the Institute was essentially born at the NASA Ames Research Center back in 1984. Greg Schmidt, Mary Wojtek, John Jenkins, John Stock, and Michelle Johnson are here with us tonight from NASA. And if there are any others here from NASA that I didn't name, they probably snuck in. But I think a 41-year partnership with the nation's space agency is also worthy of a round of applause. So we're also joined here tonight by, this evening by past Drake Award recipients. And if you wouldn't mind, as I say your name, or if I say the group that you're part of, maybe just stand up so people can recognize you. But Vicki Meadows is here. Dan Wertheimer is with us tonight. Jason Wright, last year's winner, Andrew Simeon, and recipients Paul Horowitz, John Rummel, and Bill Borucki, the man behind the Kepler space mission, are with us in the virtual event this evening. Several members of our esteemed Science Advisory Board, members of our Board of Trustees, and members of our Council of Advisors are also here tonight with us. And lastly, I'd like to welcome the Honorable Carmen Montano, who is the first woman mayor of the great city of Milpitas and the first ever mayor to attend the Drake Awards. So before I turn the podium back over to Nadia to walk us through tonight's program and get us going, like to share a little video with you to introduce, in case you don't know this individual, a famed astronomer, the first recipient of the award that bears his name, Nadia's father, Dr. Frank Drake. And please roll the film.
This array of antennas, situated in the Cascade Mountains of Northern California, is not tracing the interstellar gas of our galaxy. It's not imaging objects like pulsars, quasars, or the neighborhoods of black holes. It's searching for evidence of intelligent extraterrestrials, aliens. This endeavor is known as SETI, the Search for Extraterrestrial Intelligence. It is a daring experiment that could forever alter humanity's view of itself. An experiment to use modern technology to find other galactic inhabitants was first attempted by a soft-spoken astronomer named Frank Drake. Born in Chicago at the start of the Great Depression, Drake was interested in chemistry and electronics. He enrolled at Cornell University and was part of a Navy officer training program. After graduating, Drake was put in charge of electronics aboard a Navy cruiser, the USS Albany. In 1955, he entered Harvard as a radio astronomy grad student. After receiving his degree, the young Frank Drake joined the newly minted National Radio Astronomy Observatory in the Soft Hills of West Virginia. The observatory had just purchased an off-the-shelf radio antenna sporting an 85-foot dish, and Drake, the new guy in town, was encouraged to think of experiments befitting this instrument. What followed was a 2-month observing program he christened Project Ozma after the fictional Princess Oz in Frank Baum's book. In an experiment that discomfited some astronomers, Drake used the antenna to look for radio signals coming from the directions of 2 nearby stars, places that could conceivably house planets with intelligent beings. He wasn't studying natural processes, but looking for emissions launched into space by an extraterrestrial society. He didn't find any alien signals, but Project Ozma had generated a tidal wave of interest. A year later, Drake was encouraged by the National Academy of Sciences to convene a small meeting of a dozen scientists to weigh the odds that we could find aliens by eavesdropping on radio transmissions. The meeting was held in the fall of 1961 at the observatory where Drake had done Project Ozma. As agenda for the meeting, he wrote a simple equation on a blackboard that would estimate the number of on-the-air societies that exist in our galaxy. This agenda, now known as the Drake equation, has been called the second most famous equation in science. Thus began the modern era of SETI. Drake had planted a seed that has sprouted into several signal searches in progress today. These efforts are constrained not by a lack of technical expertise or astronomical knowledge, but by a shortage of funding. SETI is run on monies donated by a handful of interested individuals.
We will need to search through literally at least millions of stars to give us a good chance of finding a signal from another civilization.
SETI experiments have not yet found proof of extraterrestrials, but a small number of scientists are continuing the search with new observation programs and the development of new receiving equipment. By 2035, these experiments will have reconnoitered about 1 million planetary systems, an impressive sample. So it's conceivable that Drake's audacious experiment will soon pay off, that we will learn that humans are not the only intelligent species in the cosmos, that we share the universe with others.
All right, and here again is Nadia.
Oh, so as I said, Dad was many things, but he also loved and admired many things, including dinner and dessert. You heard Bill talking about ice cream. I'm going to let you in on Dad's secrets for enjoying dessert. There are 2 of them. They're easy. The first is you always eat dessert with a tiny spoon so it lasts longer. And the second is that you only ever eat half of what's left so you never run out. So if you're here with us at the Computer History Museum, we're going to spend the next half an hour, 40 minutes enjoying some dinner. If you're online, you will be treated to some chats between Marco Larsen, who's on our board of directors, and Laurance Doyle and Anne-Marie Cody, who are SETI Institute scientists. And I really hope that you can use this time to get to know one another, to ask questions at your table or in the online chat, to start forging the connections that build a stronger community. And after dinner, we will come together for the award ceremony, which is a time to reflect on and appreciate the scientific accomplishments that are getting us closer to understanding life's origin and distribution in the universe. And then we'll have a short coffee reception. And I know that if Dad were here right now, he would be looking at me with a knife in one hand and a fork in the other, signaling that it's time for me to get out of the way so that he can focus on his steak. So I will see you all in about half an hour.
Okay, I think we're back. Are we there? I think we've got Laurance and Anne-Marie available.
Sure am.
Oh, I love it. Okay,
Yes, sir.
perfect. All right, I'm very excited to first start off with Dr. Laurance Doyle, and then we're going to be chatting with Anne-Marie in just a few minutes. Dr. Doyle is a longtime researcher with the SETI Institute. He was a part of the original Kepler team that helped identify thousands of exoplanets, many in the habitable zone. He's also one of the leading thinkers on how intelligent life might communicate, not just life that looks like us, which is fascinating. He's studied the communication systems of dolphins, whales, and even baby humans to figure out what universal intelligence might sound like. So, Laurance, you've analyzed dolphin whistles and infants' cries to develop a kind of universal grammar for intelligence. Is there a pattern to how all intelligent beings might communicate? Are these dolphins our aquatic pen pals somehow? I would love for you to give us an introduction to your work and what you're doing these days.
Well, thank you. Basically, there are patterns that recognize carrying capacity, and the field is called information theory. Claude Shannon kind of invented it at Bell Labs, and they were interested in how many wires they have to string to carry a certain amount of information. When you use a zip file, you're using information theory. So information theory measures things like the frequency of occurrence and the distribution of the frequency occurrence of the signals. If you have a signal that occurs constantly, just repetitively, then there's no real knowledge being transmitted. And if you have a completely random, like reading words from the dictionary, you also have a random distribution that doesn't have a carrying capacity for knowledge or information. And there's a guy named George Ziff who in the 50s got his grad students to count, for example, in the book Ulysses, how many occurrences of the letter E, how many occurrences of the letter A, and so on down to the letter Q. And it turned out that when he did a logarithmic scale, hope this isn't too mathematical for everybody.
No, please.
He got a -1 slope, which is a 45 degree. So in other words, E was here, second most frequent was T, I think, and third is A, and so on down to Q, and -1. So he thought, that's interesting. I wonder if another book has the same thing. Yep, -1. I wonder if Chinese book has the same thing. Yep, -1. I wonder if dozens and dozens of languages, -1. I wonder if a telephone conversation in Japanese, -1, and so on. So it looked to be a characteristic of human speech. This is the first intelligence filter we can use at SETI. If you get a SETI signal and you classify the signals, you can then see if it obeys the Ziff's law distribution. Now, it's a necessary but not sufficient condition. If you get Ziff's law, then you have the potential for a complex communication system. What it's measuring is the carrying capacity. And the way it does that is it looks for a balance between complete randomness, which is a horizontal line, and complete repetition, which is a vertical line. And so that's an example. From there, once you get a Ziff's law, you can say to yourself, okay, what happens if I look at syntax within, in other words, conditional probabilities between signals? Well, it was canonical that when you got a -1 slope, that showed that humans are unique. And we had to break the news to the to the scientific community that bottlenose dolphins obey Zipf's law. That was our first real breakthrough. And then we went looking for these conditional probabilities between signals. And I'll give you an example of that. You get back to your desk and your copy was low on toner and you're missing words. And you say, I don't walk back down the hall and change the copy, or I'll wait for the secretary to do it. And so you start to fill in missing words and letters. How can you do that? The data's gone. Well, because you look at the context. You look at the context and you say, I'm missing a word. I'm going to fill it in. With high probability, you've recovered the word. Well, there's survival value in being able to recover errors in transmission, especially if you're a humpback whale and you're catching herring in a bubble net. You have to be in the right place because it's a lot more difficult. We've tried it. Believe me, it is not easy to catch a fish with a bubble. And, and the net rises and you have to have your timing just right. But they actually catch herring with bubble nets. And so they have to error recover on the fly. And the way you can do it is if there's too much boat noise or background noise, they would, one would presume, develop syntax or a kind of conditional probabilities. And so we went looking for that in humpback whales and in bottlenose dolphins, and they both have what in human language is called syntax. So this is a kind of intelligence filters that they answer the question, here's an extraterrestrial signal, how can we start to decipher it? Well, you can say, I'm going to guess, but there's no mathematical comfort in that. There's no structure. What we want to start with is information theory. And so we've been applying information theory as kind of a communicative encephalization quotient. In other words, as a proxy for communication intelligence, because communication intelligence is the kind of intelligence we're going to detect in extraterrestrials first. Does that help?
It does. In fact, I think, David, it would make sense if we're able to play Laurance's video to give us some perspective of actually what he's listening to. The idea of developing syntax through these sounds, I think, is probably foreign for anybody hearing it, at least just intuitively. And David, I'm not sure if we're able to play that now, but it would be amazing to see Laurance's sounds.
We will give it a try.
Okay.
Now, while you're listening to this, imagine it coming from space. I have transmitted humpback whale sounds and bounced them off the moon. So I do have examples of humpback whale coming from space.
Is that right?
Yeah. So when it begins to play, the basic idea is that humpbacks, for some unknown reason, even though they weigh 50 tons, that like 700 times our weight to 1,000 times our weight, they emit a lot or most of their communication in the audio range of humans, and when you drop a hydrophone in the water. And they use bubbles as tools. And we just had a paper accepted. We're going to make the press announcement within the next couple of days that humpback whales seem to emit bubble rings for humans. We haven't found them, and thousands of hours of looking, we have not found humpback whales making bubble rings for each other. But this is a kind of communication system that we're not used to. We don't use bubble rings for communication, but I thought it was amusing that in the movie The Arrival, they communicate with circular communication. So, and we've also had a previous paper where we thought we knew how to say hello in humpback, and we broadcast it, and this humpback female named Twain turned around and circled the boat, and she was not cutting off communication. We had to, because our permit was limited to 20 minutes of playback. So, we didn't know enough to explain in humpback that we had, this was red tape. But now we can broadcast for about 2 hours. And so we're looking forward to doing experiment again. But obviously a 40, 50 ton individual does not, it isn't, put it this way, they do what they please. And she was interested, and that's why she came and circled the boat. So the basic idea is that if we want to deprovincialize our approach to decoding SETI, I think it's a good idea to practice on all the languages on Earth. And humpback whales put so much of their communication into an actual audio that we can record and analyze using information theory.
So these are relatively sophisticated animals, probably more than we suspect. You once talked, or at least I read, about plants communicating to each other.
Yeah, I wrote a paper just to demonstrate.
Right.
Yeah, I did an analysis of a cotton plant that was giving air traffic control directions to a wasp. And there's a kind of a caterpillar and there's a kind of a worm. And the caterpillar is of interest to the wasp, whereas worms are interesting to birds. And the cotton plant puts out 9 chemicals, but they're different ratios of the chemicals, depending on whether it's got a worm or a caterpillar on it. And the wasps land preferentially on the ones that the plant says have caterpillars. Well, what was interesting is when I analyzed everything, the cotton plant had a vocabulary of 5. So I predicted in the paper that there were at least 3 other predators. Because why would you have a vocabulary of 5 if there's only 2 critters that are trying to harm you and you need to yell for help? Mm-hmm. Well, it turned out I got a call from the University of Pennsylvania, the insect department, or the botanical department. They basically said, you were right, there are these other predators. So I thought that was kind of fun, making predictions about, they said, how did you know? And I said, the cotton plant told me. And that's when I'm hoping to generate interest in this as a kind of a universal tool for non-human communication systems.
Okay. So how far away from a plant, or how far away is Zepf's law from an organism like a plant?
Well, yes. The cotton plant in its chemical distribution did not obey Zipf's law.
Okay.
ZIPF. And humpback whales do, and bottlenose dolphins do, and squirrel monkeys not quite. And so, yeah, the question is, can it be used? I tried it on a pulsar, Zipf's law, on different kinds, classifying different pulses from a pulsar. And pulsars do not obey Zipf's law. And as far as I know, they're the most organized in complexity, the most organized of star systems. So if a pulsar can easily be distinguished using Zipf's law from a humpback whale signal, then we've got a life detector, an intelligence detector, don't we? Now, SETI has always looked at the carrier wave. That is, if you tune onto a radio station and you turn it a dial, apologies to Paul Horowitz for this explanation. I'm doing my best.
No, and actually, if Paul's there, you should come back on and talk to us about this a bit.
Well, you tune onto a radio station and you turn the dial, and it goes to a new station. Well, nature can make an OH maser that's, I think, 300 hertz wide. So you have to turn the dial 300 times. That's the hand waving, but it gets the gist of it across. So when you look for narrowband radio signal, that's technology. So SETI has been looking for technology, and it's good because it's unequivocal as far as we know, but it's not so good because it turns out all these planets actually have magnetic fields that radio signals have to pass through, and that's going to have one of the effects is to broaden the bandpass. So in other words, by living in a planetary system with like a Jupiter, some of our transmissions in that direction are getting broadened and we wouldn't be detected.
Okay, so you're right. Okay.
So in other
Sorry,
words,
Laurance,
you
please.
need to look at intelligence instead of just the carrier wave. You need to actually say, is the message itself intelligent?
So can we back up to animals just a little bit? I'm fascinated by this. So cephalopods, they have the ability on their skin. What is it?
Yeah, receptor.
Thank you.
Yeah.
How close
Chromophores.
does that end up being? Right. Thank you.
Yeah, I actually we have a well-known octopus scientist that has visited our group, and I would love to do a 2D analysis of that. It's getting the signal type correct. I mean, if you were to, I did an analysis of a known intelligent message in Morse code, and I plot only the dots and only the dashes and their frequencies of occurrence. It gives a slope of minus 0.4. So that's almost babbling, baby babble almost. But then I thought, okay, what if I misclassified the signals? I have a dot and a dash. What if dot dot is a new signal type and dot dash dash dot and dash dash? Guess what? The Zipf slope went up to about minus 0.6. Okay, what if dot 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 is also a signal? So in other words, you can use Zipf's law to classify the signals to see if Zipf's law is hiding in there somewhere as well. So it's a pretty universal. If we get an extraterrestrial signal, we're going to be able to tell its complexity. And some anthropologists have said that social complexity is what led to communicative complexity. And what that means is that if we get an extraterrestrial signal, we might we will be able to measure its information carrying capacity and therefore possibly the social complexity of an ETI.
That's extraordinary. So in terms of organisms here, and I'm stuck on this just for a moment, I'm looking at plants, cephalopods, and ultimately whales, dolphins who are communicating. Where else on this scale are you hopeful or curious about finding that consistency?
Well, looking for Zipf's law in, like you say, octopuses or cuttlefish. And I think I'd love to apply, I'd like to see SETI Institute become kind of a center where people go for information theory analysis of the critters that they're studying. For example, I'm working on a paper now, and it compares human speech with the information theory in human speech with the information theory in human song, and then compare that to the information theory in whale song compared to the information theory in whale social sounds, and then see if, in other words, is what music is to us, is that what it is to whales? Their music is to their social sounds as our music is to our social sounds. So it will allow those kind of comparisons. And I'd like to do bee dance, since we know what bee dance means, and use polar coordinates and all. And any scientists out there want help with their critter, let me know, because it
And
all
actually,
contributes to SETI.
if you would define bee dance for me, at least.
Oh, there's a bunch of dances over the past 150 years. Nobel Prize went to von Frisch because he discovered that the bees, they go in the hive, they find a honey source, and they come back in the hive and they waggle, and they have little muscles in their necks to indicate vertical is the direction to the sun. And they waggle and turn a corner and waggle and turn a corner. And that angle that they waggle inside the hive is the angle between the sun and the honey source they're talking about. The number of waggles is how far it is. And the time they take to do it is how much the wind's blowing. So they know how much. The older bees check it out. They know how much honey to power up on and head out to the honey source. And the younger bees go, could you say that again? So, and that's they have a DVAV dance, a kind of belly dance that bees do. And that's to discuss which is the best place to swarm to. That's for internal hive politics. And they have a round dance, which is just go out and smell for honey. So we know in bee units how many, how well they can smell. And these are little guys without proper brains, you know what I mean? It's like, I think it's time to outgrow the current definition of intelligence, and in the process deprovincialize ourselves.
Well, I mean, you've said language is what intelligence does. So what do you think our odds are of decoding a real alien signal? Do you think we're closer than are we closer than we think? Are we just still kind of eavesdropping on static? I mean, you're explaining a lot of intelligence in bee dance and pretty much everything that we see in terms of animal interactivity. How close are we to decoding and understanding an alien signal?
Well, I think if you have the information theory analysis and you know the purpose of the communication, that you have a good opportunity of deciphering it. I think that given, it's interesting how, I was on Kepler with Bill and the Kepler team, and that project nailed F sub P. So that's the fraction of stars with planets. And and a lot of those planets are probably going to have significant magnetic fields. And as far as I know, that hasn't been folded into SETI yet, but there are people at SETI that Vishal, for example, that are looking into broadening the search. In other words, outgrowing the narrowband confines. But it's interesting how Kepler feeds back F sub P, fed right back into N, because it could be the planetary magnetic fields of all these planets cause a broadening of the bandpass that will require looking at the message itself for intelligent structure. Zipf's laws, Shannon entropies.
Right. And I'm wondering if you can edify all of this just a little bit in terms of where exactly your research falls within the Drake equation for our audience, sharing with them exactly where that is.
Well, what we've been talking about is F sub I. And so there's N, that's basically SETI. If you get an extraterrestrial signal, all the other terms of the Drake equation have to have happened at some level. You have to have the right star. You have to have had planet, probably, liquid water, probably, in other words. That's N sub E, that's an Earth in the HAB zone. F sub L, in other words, biology has to have happened. F sub I, it has to have got intelligent biology, and that's what we're working on. F sub C is that they built a radio telescope or optical telescope or some signaling device. Could be quantum. I think we're going to have to get quantum physics in here with its teleportation and so on. And then finally, L is how long do civilizations last? And that's the least known because we have one example.
That's the big question. Laurance, I could literally speak with you for hours.
Oh, thanks. Me too.
It's good to see you. I think you're going to have a lot of people looking you up if they haven't already.
And like I say, ask a question. I tell my students, ask a question that I haven't heard, and you get an A+.
I didn't get an A+ today. I don't know. Nick, maybe you've got something later.
Thank you. Thanks a lot.
Good to see you, Laurance. All right, let's bring in Anne-Marie, please. Hey.
Good evening.
Good evening. How are you?
Hi.
So you do some fascinating stuff. You study young stars, many with planet-forming disks swirling around them. So to a non-astrophysicist, it kind of sounds like a cosmic construction zone. Wondering if you can give us a brief description of your research. And I think maybe later we might talk about some of your drawings. I don't think we have those available to us, but would love for you to just tell us a little bit about what you're doing in terms of monitoring these stars. Not just the young ones, but maybe some of the strange ones as well.
Yeah. I mean, and speaking of the Drake equation, my work kind of spans the gamut from the earliest stars that are visible to your eye and these beautiful nebula that you might have seen pictures of from space telescopes. And those really, like you said, are construction zones. There's dust and gas swirling around these young stars, causing their light to vary quite a lot, which is my specialty. And this is where planets are forming. So it's unlikely at this stage that there's any intelligence unless there's some method for it to develop very, very rapidly. But we want to understand sort of the seeds of life, where we even came from, what happens at these very early stages, because most of the planets that you may have heard of that have been detected so far are around roughly stars of the sun's age, which is kind of corresponds to like a middle-aged person. Whereas we're looking at kind of like the babies up through the teenagers. And we're understanding how all this material that's swirling around at a young age actually comes together to form planets and then set what their future properties are. But the interesting thing is, and this is how it ties in with SETI, is that all these light variations that the youngest stars do are quite chaotic in some cases. And so again, we like to look at their behavior and say, what does this actually tell us about the system? And there's no one single behavior that these young stars do. We may be able to show some examples toward the end. But to tie it into SETI, some years ago, there was this particular star showing similar behavior to the young ones, but it wasn't young at all. At least we don't think. This is known as Boyajian star. Some of you may have heard of it. And so something was blocking the starlight. Something was going around this star, just like for the young stars, it's typically dust or a little bit of some gas. And so the idea was put out there, maybe it's something artificial. Maybe there's actually life on a planet around Boyajian star that is yet to be detected, and it's going around blocking it. I should say we don't think that's the case anymore. It does seem like it is some form of dust that we didn't expect to be there. But that has kind of launched me personally off on a search for other such systems that have things that are not necessarily planets in orbit around the stars, and we can detect them as they pass in front of the star, which is the same way we detect planets as well. The starlight goes down a little bit because something's blocking it.
So have you seen any surprising data along those lines? And we haven't discovered Dyson spheres yet, right?
Right. So we've discovered or even rediscovered a few interesting things that we're very sure are not aliens, but they are unusual. So we're looking for kind of a needle in a haystack, behaviors that stick out hard to explain with traditional astrophysics. And typically that means that the star has a fading event that's not symmetric in time. So it might get fainter faster than it brightens or vice versa. And so we have identified some unusual systems where there's something like a companion star with a huge dust disk around it, and that starts moving in orbit around the host star, and it creates a strange signal, which is not at all common. So we see things like that. And we also see stars themselves going around each other. If one's much bigger than the other, you get kind of an interesting flat bottom shape when the light dips, and then it stays low for a while and comes back up. Those are also fairly unusual.
So this is so intriguing, and we thought about a way of representing it to our audience. And so I introduced Anne-Marie to a very famous local artist in Brooklyn. Again, I'd love to bring him in right now. I'll give a quick introduction, but Aaron Alden is a composer, creative director, and his practice explores the interplay between art technology and what it means to be human, of course. Aaron uses Anne-Marie's data, real world data, to create new forms of artistic expressions, whether, weather data as a paintbrush, for example, or workout data as generative visuals, and even cyber attack data translated into music. Aaron's work has been all over the place: Lincoln Center, Art Basel, Walker Art Center, and galleries throughout New York. And I thought that getting these guys together to talk about her data and the feeds that she's seeing, that she's observing on a daily basis, and seeing what Aaron, as an artist, and that intersection would be able to come up with. And it's going to blow your mind. I love it. Aaron, maybe you want to talk a little bit about your experience with Anne-Marie and learning about her work and how this all comes about.
Hello. I don't know if you can see me. I'm in camera trouble, I think, but yeah, I've been wanting to work with SETI for a long time. I've been fascinated about finding new ways of turning data into new, exciting ways of telling stories that may be appealing to one set of fanatics, researchers, people with a personal interest. How do we take these things and make them more relevant to a wider audience? And so I've been finding ways through code and various programming sources to combine my previous careers into one sort of approach now to make art with data. So
I love that. Maybe David, we can, or actually no, Aaron, you're going to share your screen.
Yeah,
that's amazing.
So I'll share. So I took some data sets that Anne-Marie created, and we then, I hope this is working.
And Anne-Marie, you may have to talk us through some of the special moments.
Yeah, and you'll be seeing data from NASA space telescopes here. The brightness of a star over time.
So can you explain what we're looking at and what we're listening to, Aaron?
So this is Anne-Marie's data of various data sets looking at, she would know more than I would exactly where we're looking, but this is just over time and the value of light that's being emitted, which I've then turned into a algorithmic musical composition that is essentially moving a pianist's fingers across a piano, playing arpeggios within a certain set key. So the data is creating the musical output in this case.
This is an image of a young star region. So some of the stars that you're seeing in the image are doing the type of behavior that you see in the white curves.
So actually, can you play that again, Aaron? Anne-Marie, what do you love about this? I mean, we're looking at light data that's being translated into sound, obviously with some artistic license, but it's following your data.
Yeah. Well, I mean, some of it you can see when the image changes, that just the diversity and the different things that different stars do. There's one on the top that's different from one on the bottom right now. And that's telling us something else is going on in the system. So there's one right there where there's actually material crashing onto the star and creating brightness changes. It gets suddenly brighter as the gas falls in. And this is an eclipsing star system right here. There's actually two little baby stars going around each other.
All right. Does this work?
Okay.
It's kind of working.
It looks like we're guys. Looks like we are back on to the live portion, and just want to thank everybody wholeheartedly. Really appreciate Anne-Marie, seeing you, Laurance, Aaron, and all of our award winners, and Sophie. Really appreciate it so much. Enjoy the evening. Hey, Laurance, we'll do it again. Anne-Marie, same thing.
Thank you.
Thanks, guys. Talk to you soon.
Keep people refreshed and hydrated with whatever sort of hydration might be required. So thank you very much to the team for your great job. We appreciate it. I'd also like to thank our team at the SETI Institute, and a few folks in particular, for what I know, having witnessed firsthand, the sort of somewhat high level of stress and other things that go into planning and executing an event like this. So we actually have a new young gentleman with us, Tom Deardoff, who just joined us and has been the mastermind of putting this event together, and came out here because he's relocating to be part of our development team to the Bay Area from Tennessee, of all places. And he drove straight from Tennessee over the last few days to get here just in the nick of time. So Tom, great job. And he was supported by a wonderful group of people at the Institute, including Linda Ray and the Amazing Grace, who we actually do call the Amazing Grace, and Steve and Shelley and Miriam and Christine and another Christine. So a lot of people put a lot of effort into this. And so thank you all for your hard work and your great job. All right, so any NPR fans out there? Probably a few. Any fans of Marketplace with Kai Ryssdal? Right? Anybody, you know, we got some. All right, we know Marketplace. So what is Kai Ryssdal say at the beginning of that show every time? He says, and this is Marketplace, right? And he always has this amazing, perfectly timed, pregnant pause between this and Marketplace. So I'm going to borrow from Kai tonight with the following. This is the case for funding basic research. Okay, buckle up. This is not a political announcement. Allow me to make the following declaration. The House of Global Economic Dominance and Technological Leadership that the United States has enjoyed for 3/4 of a century was built on a foundation of robust funding for science and fundamental basic research. Erode that foundation and the house comes tumbling down. Silicon Valley and the stuff surrounding us in this very museum was not built by venture capitalists or constructed on the shoulders of our early technology tycoons. Silicon Valley and our tech-dominated economy was built on the shoulders of robust funding through post-Cold War defense spending by DoD and NASA and their need for advanced electronics and computing capabilities. It is estimated that every federal dollar spent on R&D and basic research yields between 140% and 300% return on investment. In other words, a dollar invested yields up to $3 in benefit. This is an enviable ROI by any standard, and it's clear that funding for science and technology have a more positive impact on our economy than any other tax dollar spent. And yet, here we are at a time when federal budgets for science are on the chopping block, with high-profile reductions for institutions such as NASA, the National Science Foundation, National Institutes for Health, while programs with little or no positive ROI go untouched. I'm all for balanced budgets, but cutting funding for science is bulldozing the foundation of our economic and technological leadership. And speaking of technology, AI didn't write this, I wrote this. All right. And please understand, this is not a political issue, right? It's not about political ideology. It's about fundamental economics. At the SETI Institute, like many academic and research institutions working in partnership with federal agencies, we are being impacted by these reductions, as are the agencies themselves. But we're more fortunate than many organizations in that our research and education programs are also supported by not only by government agencies, but also by private philanthropy and donor investors who measure ROI in terms of their positive and tangible impact on an institution and mission they believe in. Many such investors are here with us tonight, and we're eternally grateful for their support in time and talent and treasure. With financial support, while financial support powers our research, contributions of time, passion, and expertise also serve to enrich and expand its impact, connecting our scientists and professional staff to a broader and impactful community. Tonight, we celebrate science. This is not a fundraiser, but if you're interested in learning more about how you can get involved and how you can take part in humanity's greatest quest, then please reach out and let us know. We'd love to speak with you. That concludes this public service announcement. From all of us at the SETI Institute, we thank you from the bottom of our hearts for being with us here tonight. And now it's time to recognize the real stars of tonight's show, which are not on my jacket. So moving straight on to the awards portion of our proceedings, we start by honoring one of our own research scientists with the Carl Sagan Center Research Directors Award. From there, we will recognize the next generation of rising stars and then conclude with the Drake Award itself. At this time, I would like to invite, actually before I invite, I would like to thank our CSC Directors Award sponsors. This is Trustee Elizabeth Varghese and Matthew Vidon. And Elizabeth, are you here? Where's Elizabeth? Where did she go? Elizabeth, you come and join us on the stage, please. So Matthew could not be with us this evening, but I invite Elizabeth to join us on the stage for the presentation. And who better to introduce our award recipient and present the 2025 CSC Directors Award than the CSC Director herself, Dr. Natalie Cabral. Natalie, take over.
Good evening. Is it working? Yeah. So I'm Natalie Cabral. I'm the Chief Scientist of the Carl Sagan Center at the SETI Institute, and it's a great honor to present this year's CSC Award to someone whose work embodies the spirit of scientific discovery, not just through innovation, but through decades of steady, extraordinary contribution to our understanding of the cosmos. This person is Joe Twicken. Joe is one of the founders. Joe is one of the foundational minds behind how we detect planets beyond our solar system. It began with a passion for signal processing and the doctoral path at Stanford that brought him to the NASA SETI program, where the challenge was nothing less than detecting intelligence light through narrowband radio signal. He helped develop one of the most advanced tools of its time, the SETI Digital Signal Processing Engine, a chip that later displayed at the Smithsonian Air and Space Museum, a testament to its legacy. After his work on early SETI technology, Joe expanded his research, his scientific reach. For 16 years, he operated processing pipelines for NASA and ESA missions like Galileo, Mars Express, and New Horizons, missions that deepened our understanding of planetary atmospheres, surfaces, gravity fields, and the dynamics of distant world. But it was his return to the SETI Institute and his work on the Kepler mission that revolutionized exoplanet science. As lead scientific programmer at the Kepler Science Operations Center, Joe helped design and operate the pipeline that turned stellar brightness data into discoveries of thousands of exoplanets, including many Earth-sized worlds in the habitable zone of their stars. This achievement earned the NASA Software of the Year award in 2010. Today, as lead data scientist at the TESS Science Processing Operations Centers, Joe's work continues to shape the future. The TESS pipeline, building on Kepler's legacy, has led to the discovery of over over 600 confirmed exoplanets and thousands of candidate exoplanets, many close enough to be probed by the James Webb Space Telescope, bringing us closer to answering one of humanity's oldest questions: are we alone? Joe is recognized by his colleagues as a generous mentor, always willing to share his immense wisdom. He tirelessly contributes insight to Kepler and TESS data products, and his support has aided in countless discovery papers. Through it all, Joe has remained humble, rigorous, and deeply collaborative. He's a scientist who let the data speak and ensures it speaks clearly. His contribution has been foundational, not just to one mission, but an entire era of discovery. Carl Sagan once wrote, "Somewhere something incredible is waiting to be known." Joe Twicken has spent a lifetime quietly building the tools that make those incredible things visible. Joe, today we bring you into the light you never asked for, but deeply deserve. On behalf of all of your colleagues at the SETI Institute, it is my honor to present you with the CSC Director's Award of 2025.
Thank you, Natalie, for your very kind words and for recognizing my contribution with the Carl Sagan Center Director's Award. Thanks also to Elizabeth and Matthew for their sponsorship of the award. There's so many deserving scientists doing outstanding work at the Institute. This is a great honor. I'd also like to thank the dozens of coworkers that I've been very fortunate to work with. An amazing team was assembled to build and operate the Kepler and TESS mission pipelines. I share this award with the team. Finally, I'd like to thank my wife, Jill, and my daughter, Leah, for all of their love and support. I joined the SETI Institute to help build the Kepler data processing pipeline. Worked on the 2 dedicated exoplanet missions at NASA, Kepler and TESS. All the planets in our solar system orbit the sun. Exoplanets, on the other hand, are found outside the solar system. The goal of Kepler was to perform a statistical exoplanet census. How big are they? How common are they? How common are Earth-sized planets that may be habitable? This slide shows the first image that was taken by Kepler. The same exposure was captured every 30 minutes for 4 years. If you hold your hands up against the sky, the area that they cover is roughly the size of the Kepler field of view. There are millions of stars in this image. We now know that there are likely also millions of planets orbiting these stars. None of the planets are visible, however. There were a few known exoplanets in the Kepler field at the time that the mission began. One of them orbits a star named Trace 2, which is highlighted at the upper left. The number of exoplanets now known in the Kepler field is nearly 3,000, with another 2,000 planet candidates still to be confirmed. How were these planets discovered if none of them are visible? The series of Kepler images allowed the brightness of many stars to be monitored over time. As shown on the right, a planet with an orbit viewed edge on blocks a small amount of light as it transits in front of its host star. This causes a repeatable dip in the star's brightness. Thousands of exoplanets were ultimately detected in the Kepler field by searching for this telltale transit signature in the brightness measurements of their hosts. TESS is a follow-up mission to Kepler. TESS has a very large field of view, 20 times larger than Kepler. It was designed to survey the entire sky in search of exoplanets transiting nearby stars. The first image taken by TESS is shown here. Separate images from its 4 cameras are oriented vertically in the center, just as TESS views the sky. These are also enlarged in the 4 corners. TESS captures images every 2 minutes for 28 days at a time. As with Kepler, transiting planets are detected by searching for changes in the brightness of many target stars. The TESS mission is still ongoing, and a proposal has been submitted to extend it for another 3 years. My primary responsibility with Kepler and TESS has involved building and maintaining the mission pipelines. I've served as one of the lead pipeline developers. This is an artist's depiction of the Kepler science data processing pipeline. The TESS pipeline is very similar. A pipeline is a sequence of software modules which process data step by step. Images from the spacecraft are provided as input to the pipeline. Brightness is measured, a transit search is conducted, and potential planets are flagged. New exoplanets are later confirmed with follow-up observations and publication by the science community. My work on these pipelines has allowed me to help enable a revolution in exoplanet science. 2/3 of all known exoplanets today were first identified with the Kepler and TESS instruments. I've had the opportunity to work with a great team, to mentor early career scientists, and to collaborate on many discoveries and publications. Is there life beyond Earth? We don't yet know, but the search advances with each new discovery. As I conclude, I'd like to thank everyone here tonight for supporting science and supporting scientists. Good night.
Thank you, Joe, and congratulations. I just wanted to say one quick thing about the Kepler and the TESS missions, which is that if you look at your lanyard, you have the Drake equation actually written on it. And those 2 missions had a lot to say about the second variable in that equation, which is F sub p, the fraction of stars that have planets in orbit around them. And they were 2 of my absolute favorite missions to cover as a science journalist. Okay, now. In the late 1950s, when Dad conceived of Project Ozma, he wasn't even 30 years old. And in 1960, when he conducted this first scientific search for extraterrestrial intelligence, he wasn't intending to ignite a scientific legacy. He just wanted to see if his telescope could detect the murmurs of alien Earths, right? It seemed like a question that was worth trying to answer. It seemed like something that was worth trying out and seeing what happened. Now, his story of a young scientist who embarked on curiosity-driven research that ended up reshaping how we consider our own capabilities is not unique. And that is why we want to recognize and encourage the stars of the future, the scientific stars of the future, the next generation of big ideas. And that's what this evening's SETI Forward Awards do, by recognizing some of the really cool research that undergraduates are doing. And now, to introduce you to this year's SETI Forward winners, I'd like to welcome Levy to the stage. Lou is the founder and chairperson of the SETI Forward program, a founding member and current vice chair of the SETI Institute's Council of Advisors, and a longtime Star Trek fan.
Live long and prosper.
Thank you.
Hello, everyone. Welcome to the SETI Forward segment of tonight's event. I want to express a special thanks to Christine Dawood as the SETI Forward Award sponsor for this year. I greatly appreciate her support for the people that are part of SETI's future. I also want to thank Steve Bordeaux and Bill Diamond for all their support over the years to enable this award and to recognize the achievements of the students of SETI. It has been 6 years of providing this award, and I am proud to continue the tradition with this year's recipients. The mission of SETI Forward is to recognize undergraduates and encourage their continuing on into fields of research related to the search for life. All of us present today share a bond: the desire to find life outside of Earth's biosphere. Of all the sciences, biology is the one yet to be discovered outside of Earth. I certainly hope we make that discovery in our lifetime, but this is a generational endeavor. The first discovery will justify a more in-depth search. It is vital to continue the work and enable a new generation. SETI Forward is intended to help continue the search forward to future generations, to create ambassadors who demonstrate the amazing work taking place in this search, and who will eventually answer the questions that we don't even know get to ask. The answers I am personally certain of is that Earth is not the only habitat for life, and that N is greater than 1. Our first recipient tonight is Sophie Clark. Sophie worked with the SETI Institute research scientist, Dr. Uma Gorty, on the project exploring protoplanetary disk winds. Sophie plans to continue her work as a PhD student at the University of Arizona. Sophie was unable to join us in person, but she recorded this video for us.
Hello, my name's Sophie Clark. I just finished my undergraduate at the University of Florida in physics and astrophysics. And this past summer, I had the wonderful opportunity to participate in the SETI Institute RU program under the mentorship of Dr. Uma Gorty. Over the summer, I worked on a program to model protoplanetary disk winds observed by the James Webb Space Telescope. These winds are outflows of material coming from the protoplanetary disk that allow for a loss of angular momentum and thus allow the accretion process to continue and a solar system like our own to be formed. James Webb is allowing us to discern these outflows with shocking clarity, and we're now able to perform much more in-depth studies on their morphologies and their origins. I'm happy to say that I will be continuing to work on studying protoplanetary disk winds as a graduate student at the University of Arizona's Lunar and Planetary Laboratory, starting this coming fall. And I have the wonderful mentorship of Dr. Gorty and the SETI Institute to thank for this amazing opportunity.
Our next recipient is Gabby Rizzo. Gabby's research is in astrobiology with a great interest in the interdisciplinary aspects of research. To quote from her application, astrobiology is the science of developing methods to successfully detect life along with realistically enabling human habitation beyond Earth. Gabby was also unable to join us here in person, but contributed this recorded message.
My name is Gabby Rizzo, and I am deeply honored to be one of the recipients of the SETI Forward Award. The research that I was awarded for focuses on understanding how life can exist in one of the most extreme places on Earth, deep-sea hydrothermal vents. In these environments on the bottom of the ocean floor, there's no sunlight, intense pressure, and a completely different chemistry than what we're used to. Yet somehow, not only does microbial life survive there, but it thrives. In our work, we've discovered a new species of heat-loving, methane-producing microbe which we're proposing to name Methanothermococcus jasoni. It was isolated from a deep-sea hydrothermal vent in the Pacific Ocean. This microbe grows around 149 degrees Fahrenheit, uses hydrogen and carbon dioxide for energy, and doesn't require light to survive. Studying it helps us understand how life might exist in similar environments on icy moons like Europa and Enceladus, and even offers clues about how life may have originated on early Earth. But more than anything, I want to express my heartfelt gratitude. The SETI Forward Award came at a truly meaningful time for me, right as I was transitioning from undergraduate to graduate research. It's not just financial support. It's encouragement, validation, and a powerful reminder that this work matters. Especially now, in a climate where science is increasingly politicized or dismissed, support like this sends a clear message that curiosity, discovery, and the pursuit of knowledge are worth investing in. This award has given me the momentum to keep pushing forward, to dive deeper into questions about life beyond Earth, and to continue growing as both a scientist and a communicator. I'm deeply grateful to the SETI Institute and the entire community for investing in early career researchers like me. I also want to express my deepest thanks to James Holden, my PI on this research, for his unwavering support and mentorship. I also want to thank my partner in crime, Brianna Kubik, for her guidance and insights that helped me navigate this work, and to Nate Scott for all of his help along the way. I truly couldn't have done this without all of you. Thank you.
See, we are now competing with desserts too. All right, it is now my pleasure to introduce Jason Wright. Jason is a professor at Penn State, director of the SETI Center, and a former Drake Award winner. Jason serves on the SETI Forward Committee that selects our award recipients.
Thank you, Lou. It is my pleasure to introduce our next SETI Forward winner, Pritvik. Pritvik, can you come up? I was really pleased to read Pritvik's application for the SETI Forward Award. Pritvik is exploring how we can expand the search for extraterrestrial intelligence beyond electromagnetic radiation, such as radio waves or optical laser light, to gravitational waves. This idea goes back to Freeman Dyson, who suggested that there could be alien species that would use neutron stars or black holes as engines to extract enormous amounts of power. Doing this, he theorized, would create gravitational waves, which could be detected. And recently, humanity has been able to detect. Pritvik's research has involved how we can use complexity theory to detect these signals and determine that they are artificial and not necessarily natural. Speaking with him earlier today, I was very pleased to learn that he plans to continue his studies beyond undergraduate into graduate work into the search for extraterrestrial intelligence, which is wonderful because that's exactly what the SETI Forward Award was designed to encourage. He is going to use his award to attend the first European Interstellar Symposium organized by the Interstellar Research Group at a meeting in Luxembourg. Let's congratulate Pritvik on his award.
Hello, everyone. Yeah, I'm truly honored to receive this 2025 SETI Forward Award. I'm deeply grateful to the SETI Institute for this recognition, as well as the professors who I work with, Dr. Yokel Young and Dr. Stuart Bartlett at the California Institute of Technology, or Caltech. This gave me the opportunity to explore the boundaries of astrophysics, astrobiology, and SETI. Ultimately, this allowed me to develop complexity theoretic metrics for analyzing gravitational wave time series to detect signatures. And this project won the Caltech SURF program in 2024. It uses multi-scale entropy and permutation complexity to identify statistical deviations in black hole mergers signals that cannot be explained by general relativistic models. So I was invited by multiple talks to present my research findings at the Southern California Conference for Undergraduate Research, the Caltech SURF Day, and this research forms the basis for what may become a new methodological pillar in agnostic, non-biochemical SETI for life beyond Earth. I was invited as an early career convener and panelist at the 2024 Astrobiology Science Conference, the largest astrobiology graduate conference in the world. And so let's quickly go a little bit deeper. So, what is complexity theory? If you have any generic time series, you can reconstruct that time series using something called an epsilon machine. And all we're doing here, we're offering the most compact, predictive, and efficient model of any given stochastic process, meeting a certain few number of conditions that you can see above here. Now, if we go back to the previous slide, this is the generic gravitational wave signal. It describes an in-spiral of two merging bodies, two black holes, for instance, the merger event, which is the peak right up there, as well as the rim down, or the ending of the gravitational waves. That's the general signal. Now, using the epsilon reconstruction process, we can measure things like statistical complexity and Shannon entropy of that time series signal. And on the left, you can see, based on filtering the gravitational wave time series versus unfiltering that data, you have a series of statistical complexity and Shannon entropy results for given gravitational wave time series. And essentially, this allowed us to rank gravitational wave signals via their statistical complexity, via their Shannon entropy. And the ultimate goal is, let's say, imagine an alien civilization was somehow interfering in gravitational wave signals. Consider, for instance, the Zeldovich effect, where aliens could potentially extract rotational energy out of an orbiting black hole system. Consider, in another example, of an object, potentially the mass of Jupiter, accelerating from 0 to 30% of the speed of light in around 100 seconds. If such an object existed within our galaxy, we would be able to detect it today using LIGO and hopefully using complexity metrics isolated from a potential abiotic source. I truly hope such an object doesn't exist in our galaxy. And the last thing I'll quickly mention is that our next steps include adjusting the K value or the kernel width parameter of our given time series, which aids in reconstructing the process and extracting the maximum amount of information for this. And yeah, I would like to thank and acknowledge again my mentors, Professor Yokel Young and Dr. Stuart Bartlett, as well as, of course, the SETI Institute. I conducted this research under the California Institute of Technology's student faculty program, and it was funded by the Summer Undergraduate Research Fellowships at SURF. And once again, I'm truly, truly honored to achieve this award. And this prize affirms that pursuit of research is worth every single challenge. And I will continue to devote myself fully to producing rigorous, thoughtful, and impactful scientific work, and hopefully aim to contribute to a new class of SETI methodologies rooted in physics and information theory. And once again, I'm deeply grateful for this recognition. Thank you so much.
Okay, wow. Right. You know, every year I look so forward to this. It is wonderful to see these young people starting off on their careers with their futures so wide open. Today, literally to this minute, we have recognized 15 undergraduates over the last 6 years with this award. That is thanks to the support of so many, including all of you. Your various gifts, whether time, encouragement, or financial, have made SETI Forward a success. Over the last year, we have expanded SETI Forward to include a new program, partnered with SETI Institute scientist Vishal Gajah, with support from Zach Hafner, the chair of the Council of Advisors. I have worked with Vishal to establish a new aspect of SETI Forward. Vishal created an undergraduate curriculum to encourage studies and technosignature research. I am pleased to announce that Foothill College's Professor Jeff Matthews, along with 3 students, will take part in a workshop at the Allen Telescope Array. We will provide them hands-on time as part of work already taking place at the ATA in SETI research. I would like to thank Sophia Sheikh for connecting us with Foothill College and Jeff. Sophia is currently teaching at Foothill and has been associated with SETI research at both UC Berkeley and the SETI Institute. We intend to continue to find ways to reach out to undergraduate programs, encouraging the next generation to take part in the search for life. This new endeavor is still focused on undergraduates, but we are working to reach out to the professors in addition to the students. Our intent is to build more support for SETI and astrobiology research via the college professors. The work Vishal has done on creating a SETI-oriented undergraduate curriculum will help drive the curiosity of the overall community for proving my earlier assertion that N is indeed greater than 1. The Drake Awards are a celebration which has drawn us together. We are together on this journey of discovery. SETI, in many ways, is a time machine. We look to the past to discover life on other worlds. The search of exoplanets for life signatures is both looking back in time and looking to the future. To many of us, the discovery of life in another solar system is expected to change humanity's perspective. By looking in the past, we are looking to shape our own future. I encourage everyone here, whether in person, virtual, or watching a recording, to take part in the many aspects of the SETI Institute's research. There are many ways to contribute, and the SETI Institute team members want to hear from you. I can tell you that giving to this cause is personally rewarding. With all the challenges ahead, I encourage you to find a way to help. It is amazing what small things can become. Before I close, I want to express my thanks to 2 other people. Without them, SETI Forward would not have happened. To Jill Tarter, Jill, you have always been there to encourage the recipients and myself. From the roots of this at UC Berkeley, you have been an encouragement to me and this program. I also want to call out Dan Glasgow, who helped make this all possible from the time we first established the endowment. Dane's generosity and inspiration of others is the primary reason we have this endowment, helping create a sustainable program. But most important of all is our award recipients, both past and current. I wish you all the success in this and other worlds for your careers as you seek the questions and answers to unravel the great questions of the universe. Thank you all.
Thank you, Lou, and congratulations to all of you. We are now at the moment you all have been waiting for, which is the presentation of the Drake Awards, which are given in recognition of exemplary contributions to the field of astrobiology or the search for extraterrestrial intelligence. Now, as Lou said, of all the fundamental sciences, biology is the only one that we have yet to discover beyond Earth. But the truth is that we don't really have a good understanding of biology even on Earth. And I can say that because I have a PhD in not understanding biology. We are continually surprised by life's resilience, its tenacity, its ability to find a way. And our quest to understand life's origins necessarily spans both space and time. We look here toward our own world in search of life's terrestrial cradle. And we look outward toward other worlds in search of the extraterrestrial cradles that might tell us something informative about ourselves. And we use the lenses of science to look back in time across the sweep of eons to try and understand the spark that transformed a pool of raw materials into replicating cells with metabolic furnaces. Too often, I don't think we pay enough attention to the search for life's origins. But tonight, our origin story is about to take center stage. This year's Drake Awards are sponsored by Avery Wong and Katya Rolt Wong and John and Carol Ginandrea. Thank you. And to help us celebrate our award winners, John Baross and David Deamer, we've prepared a short video tribute created by filmmaker Kelly Kowalski, who has beautifully captured their inquisitive nature and the importance of their work. This video is an absolute treat. From their groundbreaking research to their influence on the scientific community, the video offers a glimpse into why David and John are so deserving of this honor. Please enjoy.
Do you hear me? Give my creation life!
Are you sure this is how they did it?
This is astronomer Frank Drake. He had an equation, a probability argument about life out there. R asterisk. How many stars born every year in our galaxy? Perhaps 6 or maybe 7. FP. How many stars have planets? Probably most of them. And E. Number of planets within those systems that support life. Likely 1, maybe a few. FL. Those planets that actually have life. FI. How much of that life is intelligent? FC. How much of that smart life develops technology? And L. Does any of that intelligence survive long enough to talk to each other? For this story, we will focus on FL, the probability of life developing on a planet. Confirmed number 1. Number of scientists figuring out the origins of life on this planet. Officially a few hundred. They have a logo. Here are 2 of those scientists. This one suggests that life erupted deep beneath the sea. This one suspects life bubbled up in a hot little puddle. Both are astrobiologists, advancing the study of life here and beyond.
We're doing a recipe for the chemical building blocks of life. And today I have turned my kitchen into a biochemical laboratory to show you what some scientists think could have been nature's recipe for life on this earth. And perhaps life in the rest of the universe.
This is a meteorite, the Murchison meteorite. It fell to Earth in 1969. here in Murchison, Australia. It contains stardust that's 7 billion years old, older than our solar system. It's loaded with ancient organic compounds that came from outer space. This is Deamer, David Deamer, a prebiotic chemist and biomolecular engineer with a penchant for the possibility of panspermia. When Deamer doused a sample of the Murchison meteorite in water, he discovered ancient lipid molecules that spontaneously arranged themselves into little round vesicles. Just like a cell membrane, thought Deamer. The implications of this eureka moment: lipid molecules, wandering through space on their own accord, arrive on a watery, rocky world, and while bathing in H2O, those lipids spontaneously organize themselves into cell-like structures, a cozy cocoon for the chemical complexities of prebiotic life. Deamer published his discovery, but without much notice back then. Sure, cells are a neato concept for life to happen, but how do you get all those other ingredients into those protective protocells? Kamchatka, Russia, the most active volcano region in the world. There are more brown bears than people in Kamchatka. Deamer was pondering Darwin's warm little pond theory. What about hot frothy puddles, thought Deamer. So Deamer dumped some raw materials for life in one of Kamchatka's hot little puddles. And wait for it. Poof, within minutes, there at the edge. Membrane-like bubbles that encapsulate those raw materials for life. So Deamer's origin theory? When the water evaporates, those bubbles break up into layers of lipids, with the raw materials in between. Rehydrate and voila, those lipids spontaneously spring back into vesicles, pregnant with the potential for life. Sure, it might take a few billion false starts of random sequencing, but rehydrate and dehydrate enough times, and you might just get the right combo for the makings of primitive cellular life. And that was a breakthrough that got noticed. Did volcanic hot springs harbor the first living organisms? Or instead, did life emerge from deep below early Earth's oceans?
Supposedly, Cousteau and his cronies invented the idea of putting walkie-talkies into the helmet. But we made ours with a special rabbit ear on the top so we could pipe in some music.
The deep sea, a world of crushing pressures, extreme cold, and darkness. No sunlight, no photosynthesis for life. Here, hiding at the bottom of the seafloor, a hydrothermal vent, a very hot, hot spring erupting between Earth's tectonic plates. This is Alvin, a submersible that has made over 5,000 deep dives since the 60s. You can fit one pilot and 2 scientists on the inside. When word got out about some temperature anomalies off the coast of Galapagos, an Alvin crew went to investigate. And what a surprise. They discovered an entirely new ecosystem flourishing in the clouds of black smokers. Not smoke, but microbes, metabolizing energy from the chemical chaos seeping out of the smokers. And eating those microbes? Fantastic creatures galore. And this human creature, John Baross, a marine microbiologist with a soft spot for seemingly uninhabitable environments that turn out to be habitable. Baross asked the Alvin crew to save samples of their extraordinary find, the only available preservative, their ship's supply of rum and tequila. Or so the story goes. After analysis of the samples, Baross and colleagues posited a radical theory at the time. They suggested these deep-sea vents are the perfect chemical reactors for abiotic synthesis. In other words, a laboratory for life. At the time, a leading origins of life researcher poo-pooed it. But you cannot suppress the evolution of scientific theory. The Venn hypothesis stuck, and with it, our fundamental understanding of life. As it turns out, life thrives in all kinds of alien environments. Take your extremophiles, for example. You got your acidophiles, loving their acid lakes. You got your psychrophiles enduring below freezing temperatures. How about this square-shaped halophile that thrives in extremely salty situations? You find Deinococcus radiodurans in nuclear waste sites. And the beloved tardigrade, surviving all kinds of extremes. with its unique superpower, inducing near-death experiences, only to spring back unscathed. And Baross's expertise, thermophiles, thriving in high temperatures as hot as 122 degrees Celsius. Only a day after Mount St. Helens erupts, you'd of course find the intrepid Baross probing for thermophiles, just minutes before another eruption. In fact, given his reputation for following life to the extreme, Baross was asked to chair a scientific committee to define the outer limits to life as we know it. The results published here, aka the Weird Life Report. Because if you're going to be an astrobiologist in search of alien life, it's probably best not to mistakenly miss it. So, now that we know, thanks to our friends the astrobiologists, that Earth life is way weirder than we first imagined, emerging from extreme ecosystems and exploiting ever-changing environments. So how then do we search for so-called alien life? Do we look for its evidence around ancient hydrothermal fields like those we find on Mars? Or go below the deep, icy oceans of Europa in search of hydrothermal vents? Maybe some methanotropes feeding at the shores of Titan's methane lakes? And don't forget our exotic exoplanets. So, if we've learned anything here, let's not be so terracentric, because the building blocks for life, literally, litter the universe. And the probability for life to develop on a planet? 1, 2, or how about infinity?
All right, how cool is that video, right? That's fantastic. Is Kelly Kowalski here? Kelly, can you please stand up? Our filmmaker, Kelly Kowalski. So, want to thank Kelly for that great work. And how many of you were at our 40th anniversary party in November? Fair number. All right. Well, Kelly, if you may recall the amazing video biography that Kelly put together of Jill Tarter was all equally extraordinary. But I think one of the interesting things about this video that I think is a really kind of clear and unequivocal message is that, you know, in our world, the science fact is even more interesting, more wild, more wonderful, more beautiful than the science fiction. It's really quite extraordinary. So we're going to stay on the theme for the moment about the intersection between art and science at the Institute. And you may have noticed this strange object off to my right here, covered with a black veil. And you know, you might wonder if this is the first portrait of an alien civilization. Sadly, it isn't, but it is something quite extraordinary. However, I have to just stop here, and this is where my team again is going to be pulling their hair out. Thankfully, they're not pulling my hair out, but because I just have to go back in time a little bit to the extraordinary students we honored tonight with the SETI Forward Award. I mean, these young people are just amazing and inspiring. And I thought, you know, the videos were incredible. And Pritvik, how many of you understood what Pritvik was talking about? Show of hands, 3, excellent, 4, 5. There will be a quiz afterwards. But there's something I have to share with you that I think is worth sharing and taking this pause for a moment regarding Pritvik and his application. You know, the undergraduate internship program at the Institute is really an extraordinary and wonderful program. It's also highly competitive. We get over 450 applicants for about 12 places. So statistically, this is harder to get into than Harvard or MIT or Stanford. But, and I have to say, it's a terrifying honor to be the head of an institution that runs a program I could never get into. So, but these young people are really extraordinary and they're gifted. And I only wish we could support all 450 applicants. But I want to say something about the application that came from Pritvik and the letter that came from the faculty member at Caltech in support of his application for this award. It made reference to somebody that I would guess most of you have heard of here before. His name is Albert Einstein. A professor at Caltech referenced this young man as having Albert Einstein's kind of brilliance. I think maybe we saw some of that come through tonight. But the reason I point this out is we might all want to take our time to just stop and say hello to Pritvik, because someday he may be famous, more famous than all of us put together here. But anyway, that's the kind of people and young people that are doing the extraordinary work here today.
All right, Bill.
All right. So
I think we probably want to show them what's in.
All right. So let's, without further ado.
Which I don't even know what this is.
We don't know what it is, except.
We're going to find out.
So we have an artist in residence program at the SETI Institute. And the purpose of this program is to explore the intersection between art and science, and to give the opportunity for the interpretation of science through the lens of the creative process. And so we actually commissioned one of our artists to do an artistic rendering that is representative of the science that has been done by our 2 award recipients tonight, John and David. I haven't even seen this yet, but this is a gift to the Institute, and there's also a version of this for each of our award recipients. So we're all going to see this for the first time. I don't know if there's anybody who could do a drum roll, but this is a tribute to our program and our award winners this evening. There you go.
What do we have? That's oh. What are we looking at? Okay.
It's an animated version of this.
I see a cell cycle. I see, gosh, flowers, some bacteriophage. Like what? Interesting. There are viruses there. Mitochondria. Bill, do we have a video that might give this some more context for folks?
In theory, we do have something.
Wow.
Yes. So we do have some thoughts to share from the director of the Institute's program, the AIR program, Bettina Forget. Bettina?
Hello, my name is Bettina Forget. I'm the director of the SETI Institute's Artist in Residence program. I'm sorry I can't be with you in person today, but I do want to take this moment to congratulate our distinguished Drake Award recipients, Dr. David Deamer and Dr. John Baross. Bravo to you both. Your work explores an intriguing question that touches on science, philosophy, and the imagination. What is the origin of life? It's a question that fired up the imagination of our invited artist, Dr. Jennifer Willet, who has created the wonderful collages and the animation that you are seeing tonight. Jennifer is an internationally renowned artist whose work combines fine arts practices with applied biotechnologies. She made a tailor-made artwork for tonight's event to bring our award recipients' research to life. I love that Jennifer's collages transmit a sense of wonder and discovery. And while her work looks colorful and playful, it is grounded in scientific research. In fact, Jennifer had conversation with both David and John before starting her composition. And if you look closely, you'll find visual elements that are directly quoted from both scientists' research. This close connection of art and science is central to the SETI Institute's Artist in Residence program. I always like to say that our Artist in Residence program transforms data into experiences. Artists can provide innovative, unique perspectives and new ways of understanding complex scientific research. And it's just a delight. I hope that you'll delight in tonight's conversations, discoveries, and Jennifer's artworks. Enjoy the rest of the event. Greetings from Montreal.
Our lovely piece, and we'll have this on display as well in the coffee reception afterwards, so you can take a closer look. But I do think it's a wonderful attribute and opportunity and privilege for the Institute that we can bring art and science together. And again, look at the science that the Institute and its researchers conduct through the lens of the creative process and all kinds of art, from music to the visual arts to choreography and beyond. So very, very exciting to do this. But now I think it's time to move to the Drake Award presentation itself. So Nadia is back on stage with me, and I'd like to also bring up Dan Langford, the chairman of the board of the SETI Institute, to help us with the presentation. As Dan's coming up again, although Nadia said this once before, I want to once again thank our sponsors for this award, Avery Wang and Katya Raoult Wang, and our trustee as well, John Andre and his wife, Carol. So thank you again very much for your generous sponsorship of this award. All right, so you've had a little chance to meet John and David. Hopefully some of you had a chance to meet them both this evening and chat with them informally. You've seen a little video profile about them. Now, I want to give you a little more of the statistical biography of both gentlemen. But John, as you can see from the video, Baross's research focuses on understanding life in extreme environments, particularly deep sea hydrothermal vents, where some of Earth's earliest life originated and formed. But his work extends beyond Earth and has helped shape the search for life beyond Earth on planets and moons with comparable conditions. Professor Emeritus, the School of Oceanography and Astrobiology program at the University of Washington in Seattle. John started at San Francisco State University, stuffing off with degrees in microbiology and chemistry, then on to the University of Washington for MS and PhD degrees in marine microbiology. After a postdoc and faculty positions at Oregon State University, John moved to the University of Washington and there was one of the founding members of the astrobiology program. We're proud to note John formerly served on the SETI Institute's Science Advisory Board. He's a fellow of the American Academy of Microbiology, associate member of the National Academy of Sciences, and the 2022 recipient of the NASA Exceptional Scientist Medal. So welcome, John Baross, if you could please join us up on stage. Dr. John Baross. Stay right here, John. All right, and Dave Deamer. From the cosmic origins of life to nanopore gene sequencing, David Deamer's work has made vast impacts on numerous fields. An emeritus professor of biomolecular engineering at the University of California, Santa Cruz. Dave started his academic career with a BS in chemistry from Duke University and earned his PhD in physiological chemistry at Ohio State University School of Medicine. A Guggenheim Fellow enabled David to work with Murchison meteorite samples, as you saw in the video, at the Australian National University. He's the author or co-author of over 200 research papers and review articles and at least 12 books, including Origins of Life, First Life, and Assembling Life. Welcome, Dave Deamer.
Congratulations.
All right. So for each of these gentlemen, we have a medal, the SETI Institute Drake Award medal that will be actually Dan Langford. So that's for David.
What?
And for John. Whoops. Here. Again, this is the certificate for John, and Nadia, I'll give you the certificate for David.
Yes. There you go.
And for each of these gentlemen, this award comes with a $25,000 prize. And both gentlemen are putting that $25,000 prize to work in nonprofit research supporting the science that means so much to them. Congratulations. Thank you so much. Thank you so much. Our Drake Award winners. What a great honor and privilege to recognize both of these gentlemen. And I think we have
Yes.
something else to share.
So in place of more traditional acceptance speeches, we thought it would be fun to treat you all to a short conversation with our 2 Drake Award winners. So if you would come over and have a seat. I will be moderating a short discussion. We're going to aim for maybe 15 minutes with these 2 gentlemen. And I just wanted to say that it's such a privilege to be here on stage with both of you. Your bodies of work are incredible and thought-provoking. And as I said, I feel like the search for life's origins is often kind of an ignored part of astrobiology. And so it's really nice to be here on stage with 2 of you who've thought about this for a long time. And my first question for you is just simply kind of, how are you feeling? Like it's really been an evening. So how are you feeling? How are you doing?
I have to have that
Microphone. Can you, okay, we're going to use the microphone. Yes.
I have to have the
Yeah.
question repeated.
The question is, how are you feeling? How are you doing right now?
Oh, am I right now?
Yeah.
I'm happy.
Okay.
Is that all?
Yeah, well, I don't know. I mean, like I'm ready for a glass of wine. I don't know. Like, John, how are you?
Oh, I'm ecstatic over all of this, and it just it's I can't say it in a few words, but there are so many people here that I have known from the past associated with SETI, including people like Jill Tarter and Natalie and Bill and et cetera, and Andy. And it is just so great to be back with all of them. And what a great pleasure. Thank you for all being here.
Yeah, thank you, everybody. John, I wanted to ask you, the video that we just saw showed us an image of a hydrothermal vent and said that these vents were discovered in 1977 and that was a revolutionary discovery. I think that kind of undersold it a little bit, because I have heard the discovery of hydrothermal vents described as the first time that we found life as we did not know it right here on Earth. And so I'm curious, what was so surprising about finding those ecosystems?
The most amazing thing about the discovery of hydrothermal vents, which are between now 2,000 and 5,000 meters deep in the ocean, okay? Very deep. And we don't expect to see much life down there. And here are these communities that are more abundant and rigorous and diverse than we see on the surface. It was just amazing. And how are they eating? What are they feeding on? And so this is the first time we were realizing that what was coming out of hydrothermal vents included things like hydrogen sulfide and hydrogen and methane. And these animals have microorganisms associated with them that are utilizing those as energy sources, fixing carbon dioxide. So these are the deep sea symbiotic community. And we now know there's over 350 different animal species down in these vents. And, they're living off completely different situations. I will make one more comment. As you know, animals rarely live among past, let's say, 40, 50 degrees Celsius, which is the highest temperature. And the highest temperature growing animal that we know of is in hydrothermal vents. And it's I'm not going to go into it, but their biochemistry is extraordinary. That allows this animal to grow at temperatures that are amazing. So anyway, I don't want to go on, because these vents are just remarkable. They're just amazing.
Yes.
Absolutely, I agree. When I first heard of Jack Corliss's discovery, and then your paper in 1981, I believe, with Sarah Hoffman, that was a revelation. So no doubt in my mind that we need to know as much about hydrothermal vents and the organisms as possible. But we say they are not dependent on sunlight, directly at least. And indirectly, though, they're dependent on the oxygen made by photosynthesis. So that's what we have to recall here, is that even though these are extremely unusual animals, they're just like us in another way, that they depend on photosynthetic oxygen.
There's only one group of animals that I know of that grow without oxygen.
Which
I'm not gonna
is,
mention that.
what
You're
is
right. I
that
mean,
group?
David is right on that, and
Microphone.
but I'll end it. My point, I'm a microbiologist, so when I went down, my excitement was, what kind of microbes are growing down there? And do I have time?
I can't see our timer right now, but can I ask Dave a quick question first?
I mean, this is my,
Okay, go for it. You have time.
You're scratching my intellectual back here. Yeah, when you're hitting what I love to do more than anything, so. Okay. One of the things that I've been interested in is microorganisms that grow at extremely high temperature. And also those microorganisms that may actually have a genetic makeup that tells me something about what the earliest microorganisms on the planet look like. And and I've been part of that, a part of that research. So the highest temperature microorganism that's been ever found is found in vents. It grows at 122 degrees Celsius. Grows at 120 to 22 degrees Celsius. So it's high. Recently, there's a group of archaeal type group. There's bacteria and there's archaea. They both look like bacteria, but archaea are different. And organisms that make methane, for example, are archaea. They recently found an organism that is called Lokiarchaeota. And now I'm going to explain why that just blew me away. It blew me away for a couple of reasons. One is that the origin of a eukaryote, the origin of a cell like makes up us, is made up of an archaea and a bacteria. So somewhere along the early evolutionary line, an archaea picked up a bacteria, and that bacteria became a mitochondria. Now, we've never really known what kind of archaea was that. When the Lokiarchaeota was found, it actually had genes that are very similar to what are in these higher cell organisms, including those that can take up another organism. It's just mind-boggling when that came out in 2015. Since then, others related to that have been found, again in hydrothermal vents, including what we think now is the earliest microorganism that led to a higher organ. I'm going to stop here.
Okay. I think the take-home message is that hydrothermal vents are these incredibly interesting ecosystems that really stretch our ideas about the limits of life on Earth. David, I wanted to ask you, in the video, we saw you in Kamchatka near a volcanic puddle dumping some stuff into it, which in theory could lead to life. What do you think is happening in that puddle now?
Yeah.
What happens if you go
Something
back?
crawling around there that shouldn't be. Well, I anticipated this question would probably be asked, and I brought a can of primordial soup. And on the can, they must have been reading my papers because they say that these contain amino acids, purines, pyrimidines, and fatty acids. And that's what I poured into that puddle. So they knew that we were onto something. These guys, this is Wallace's soup. He also threw in some tomato soup, so I'm gonna pass on that. The point though is that if we give this kind of a mixture of things, John and I agree that at some point there's going to be a more complex structure grow out of that. And this summer, we are making RNA from scratch using what I learned from that pool. It's what we call a wet-dry cycle. It turns out that nucleic acids self-assemble under those conditions into long strands. We're going to see if they can reproduce. And we are going to use nanopore sequencing, which was invented at UC Santa Cruz. We're going to be using nanopore sequencing to watch for copies appearing where they could not be unless there was a template directed polymerization. Now there's a commercial aspect of that. We're applying for a patent, of course, proprietary patent. And I have a little company called UpRNA. And if any of the venture capitalists in the room would like to see my deck, I'll pass it right along.
All right. So we have time for one more question. Before I get there, I just want to know, does that can have an expiration date on it? How long is it good for? I'm just kidding. The question that I want to ask both of you, because it's the one that weighs on my mind when I think about the origin of life here on Earth, is how will we ever know what that origin was? How can we know?
Let me start with the answer.
Please.
I'm going to change one vowel in what you said. And that kind of makes it all possible in our minds and just as a way to teach people about this. We will never understand how life did begin, but we can understand how life can begin because we think we're on the way to making a primitive version of life with a replicating system in the laboratory. That would be, by the way, we have competition on that. Jack Szostak is hard at work, Nobel Prize winner. So we're competing with some very high level people in this, but we're all on the same trail that we think there is a relatively simple way for nucleic acids to begin to reproduce almost like viruses do in our cells when we catch a viral infection, but instead they will have infected the earth and found out how to use the energy and resources to reproduce without life in a cell.
John?
This is such a complex question for me. I did was involved in writing a paper on the origin of life and potentially invents. I no longer believe in that. It's much more complicated than anything that I could imagine. And while Dave and, as he mentioned, Jostek and others that are looking at the RNA world and trying to get RNA in a membrane and get some replication, Dave is correct. We don't exactly know how it may have formed on the Earth. So I've been taking a little bit different direction and trying to understand the earliest life that happened on Earth, earliest evidence for life, to what the earliest organisms that are our ancestor really look like, something we call LUCA, the last universal common ancestor. And we have some evidence that, very strong evidence that LUCA was an organism that made either methane or acetate and has a specific pathway that we think is really ancient. Okay, so we have that. And then we go back to what is the earliest time when life started? And there's different ways of looking at this. There's certainly no question there's fossil records at 3.4 and 3.7 billion years ago, but there's evidence from isotopes of even 4.1 billion years. So what did Earth look like at 4.1 billion years that allowed life to exist in such a way that it altered the isotopes of carbon that made it look like life existed? So I've been kind of trying to put pieces together like this and say, all right, what were the kind of environmental setting that may have started producing the complex sort of chemical interactions that have gone on? And I won't go on in this, but I have some other little models in my head about how this might be working.
Well, I would love to talk with both of you for so much longer. I have like 15 more questions on here. But we are actually running a little bit over time, so I'm going to close this discussion now. I hope I can catch up with both of you again soon, and all of you can maybe catch up with them for some questions as we wrap up. But I wanted to just reiterate something that Bill said earlier about science and the fact that the science it takes to answer such fundamental questions about who we are, where we came from, the cosmic context in which we and Earth exist, that science is also fundamental to our society, right? And everything that we cherish, economically, technologically, it has its roots in the fundamental sciences. And historically, there has been a very close and mutually beneficial relationship between science and donors and benefactors. I like to say that even Galileo had his benefactors. And so I think it's just important to remind everybody that now more than ever, it takes all of us to participate in the scientific process and in the process of discovery, so that we can hear from people like the two of you about this really transformational work that you've done. So thank you. And Bill, I know you're back on stage for some closing remarks, so.
Thank you, Nadia. And let's hear it again for John and David.
Yeah.
So what is the life cycle and birth rate of a star? How many stars have planets? Of those planets, how many are in the habitable zone of their host star? And if there are habitable environments, in how many cases does life emerge? Is life maybe even an emergent process? If life emerges, in how many cases does intelligence arise? And if intelligence arises, in how many instances do evolutionary processes have enough time for the creation of a technological civilization? And if that happens, how long does the technological civilization remain detectable for whatever reason? These are, of course, the questions of the Drake equation. These are the questions we address every day at the SETI Institute. And this is one of the most wonderful and extraordinary and exciting things from my perspective in particular, that it makes it so such an amazing place to be, is that it embraces almost the entire spectrum of the natural sciences. This is an endeavor of one particular branch of science. This is an endeavor of all the branches of science and the branches of art and culture and society and all the rest. So I think one of the things we hope you take away from tonight is we may be on the verge of answering the question, what is the origin of life? We might be on the verge of answering the question, are we alone? And you heard it here first tonight, but it's getting very close, is it
One
not?
of those answers is in that can right there.
One of the answers may well be in the can, as Nadia points out. Well, something that has happened for the first time in the history of the Drake Awards and the first time in the 40-year history of the Institute, it's not even on the program because it's so spontaneous, perhaps like life itself. But since we were privileged enough to have the mayor of Milpitas join us tonight, she provided a City of Milpitas commendation for both of our awardees, for Dr. David Deamer and Dr. John Baross. And for the SETI Institute.
Nice.
How cool is that? Thank you very much, Mayor. Thank you to the City of Milpitas. Thank you to our award recipients. What an extraordinary night. And
Thanks, Bill.
great job as always.
Thank you, everybody, for being here. It's been such a pleasure to spend the evening with you.
So we're going to do one other fun thing, because how often do you get a chance to do this from the stage? I'm going to take a picture of all of you saying hello and congratulations to John and David and Nadia too while we're at it. But how about everybody waving hello? That's awesome.
That's actually a lot cooler than I thought it was going to be.
Right?
Yeah.
That's pretty cool. All right. Nadia
really
was thinking
cool.
like, oh, this is corny.
It's like,
But
gosh,
that's-
Bill. No, that's going to be a cool shot.
That's going to be a good shot.
Yeah.
All right.
All right.
So from inspiring, interesting conversations from well-deserving recipients to or recognizing the next generation of scientists, I think and hope you have enjoyed this evening. I want to do, and again, a special thanks to all our speakers, our honorees, our sponsors, the team here, the team at the museum who made tonight's meal so possible, and of course to all of you for being here to share this evening with us and to share this evening with our incredibly deserving recipients. So if you're feeling inspired, please stay in touch, get in touch with us and learn more, find out what we're doing, what we're up to, and if there's something about the work that we do that connects with things that you're interested in. But we hope you had a wonderful evening. We wish everybody a safe journey home. We do have a coffee reception outside, so we can get caffeinated after being wine-inated.
I would like to be wine-inated first.
You want to be wine-inated?
I would want, yes.
Okay, we
Between
get wine-inated and then caffeinated.
Yes.
But thank you all very much. I would like all of the award recipients and those of you who were on stage for any part of tonight to come forward, because apparently we have a photograph that we need to take. So please come up on stage. And with that, that concludes the formal part of tonight's proceedings. Thank you again, Nadia. Thank you, John. Thank you, David. Thank you, all of you.